Thank you, Jean-Baptiste. Thanks, everyone. Welcome to my presentation about experimental insights into dynamic fire behaviors. And first, I would like to thank Jean-Baptiste Filippi for giving this opportunity to present today. And compared to the previous presentation, this one will be small in scale, I would say more specific, targeted to fire behavior at smaller scale, but in the field as well. Very short outline, introduction. I'll talk about emerging fires, and after that about spotting in wildfires, provide some experimental data what we've got. First, I represent Flare Wildfire Research Group at the University of Melbourne, and in our group we have several research topics, let's say, we're working on. Fire behavior, landscape flammability, ecosystem interactions, fire risk modeling, and future fires. I'm leading fire behavior theme, and I will be talking about that. So what we do, what our group does, we aim to provide a strong scientific foundation for predicting fire behavior and assessing the impacts of wildfires on landscape and communities. And for today's presentation, I will cover some of some of the research we are doing on dynamic fire behaviors and previously called, still called, extreme fire behaviors. So what does it mean? Dynamic fire behavior is a physical phenomenon characterized by rapid changes in fire behavior that occur under specific conditions and can be identified, described, and modeled. And currently there are several dynamic fire behavior recognized, not all of them on this slide, but some of the examples you can see here from spotting, fire-generated vortices, fire wheels, paraconvective events, crown fires, conflagrations, emergent fires, eruptive fires, and so on. In today's presentation, I will be covering only a few of them. I'll start with emergent fire fronts. If you don't know what it is, emergent fire fronts is a convergence of multiple fire fronts from a single fire, or separate individual fires into larger fires. And you can see some of the examples here. They could be fire coalescence, junction fires, inward parallel fire fronts, fire coalescence when multiple spot fires merge together, a junction fire, specific configuration of fires when two fire fronts merge together as in a V shape, you can see here, and usually they characterized with a junction angle between two fire fronts, fire legs, which are basically one side of the V, and parallel fire fronts by length of fire fronts and distance between them. And in our group, we've done quite a lot of field experiments on emerging fires. And the reason for that currently there have been a lot of studies on emerging fires, mostly at the lab scale. And from observing real fires, we know that it's not easy to upscale lab results to the field and real size fires. And sometimes we see some discrepancies between these results. And we wanted to see if fire behavior characteristics defined in the field are similar to what we observed in the lab. And you can see some of the locations where I did experiments. This is close to Melbourne in Victoria, Australia. And we've done experiments for in the last 5 years and different fuels. You can see some of the type of fuels we did testing. We did experiments in heathlands, which are similar to shrublands, where shrubs from 0.5 meter to a couple of meters, heathy woodlands, grasslands, and also harvested croplands or stubble burns. So we wanted to investigate how fire behavior changes in different fuels and how that affects on emerging fires. And these are real examples of different configurations of emerging fires. You can see, I don't know if you can see my pointer. This is example of junction fire. As you can see, V-shaped fire with rate of spread propagating downwind. Parallel fires, inward parallel fires. We call it forward junction fire when fire propagates downwind, and against wind, it's backwards junction fire. Yeah, excellent, thank you. And this is fire coalescence when two separate fires merge together. And in our experiments, we use a bunch of different equipment. We developed and designed custom designed fire behavior packages which allow us to measure heat fluxes, wind speed and direction, temperatures inside fire. They're portable. We use infrared cameras. We use drones with infrared and visual cameras dual. And we use different weather stations, portable and also position in specific locations for the whole experiment. And usually we record data with 1 Hertz frequency to get more or less sense what's happening in the fire, because fire is very dynamic. It changes quickly. We need to have at least one second resolution to get that. Yeah, some of the examples how we deploy equipment. Pictures of me everywhere, so it's kind of promoting myself. And this is example of how we deploy our fire packages. You can see configurations, and we can measure, as I mentioned, wind speed and direction, temperature, convective, radiative heat fluxes, total heat fluxes in those particular points where we position sensors. And when in previous presentation was mentioned that it's challenging to measure fire behavior, I know that it's really difficult because especially in large field scale fires, when you have a lot of equipment and for some reason some of it doesn't work at the end, you have a bunch of packages, and after the fire only half of them or part of them worked, and this is a real challenge. And examples how we deploy our packages, 22, 23, series of experiments. You can see the example of heathland. This is grassland fires. Some of the videos of fireland ignitions we did. Usually we work with fire agencies when they do prescribed fires, but because of the agreement, they can do fires. Usually in prescribed fires, they burn against the wind to reduce the intensity. But in our fires, we always do downwind, similar to real fires. And you can see some videos, stubble burns of heathland and grasslands at the bottom. Oh, pardon. Yeah, this is example simultaneous video and infrared of heathland fire. You can see fire agencies, fire crew ignited, V-shaped fire, and fire starts to propagate. Probably accelerate a little bit. And we use all this information to define, for example, the areas of active burning, flaming combustion, smoldering combustion, temperatures distributions, and also heat fluxes from our packages. And one of the outcomes, you can see, for example, comparison of fire line intensity by Ram's equation during evolution of the junction fire. So it starts, we make it dimensionless from 0 to 100% of time, basically 0 when we ignited our lines, 100% time when junction fire merged and became just a straight line as regular head fire. And you can see that fire line intensity constantly increases up to 75% of time, which was the case when we wanted to investigate it. So basically it shows that fire constantly increases its intensity during development, and only at the end it kind of reduces its intensity, which could be a very dangerous situation in real life. This example of temperature distributions inside the combustion zone. What we did, we selected along the fire front a buffer zone, and we analyzed temperatures inside those buffer zone, how they change in time. And you can see that again from 0 to 100%, basically from start of the fire to the end of the fire, temperatures in different ranges, they constantly increase during fire development. So that tells us about depth of the fire front. Basically, we call it deep flaming. Depth of the front increases, intensity increases, and again could be very dangerous for firefighters. Another examples of the data, you can see here heat fluxes from fire behavior packages at different times of fire development, 25%, 50%, 75% of fire development. And you can see that heat fluxes, they again increase as fire progresses or develops, let's say. And this video shows, again, junction fire development after ignition, and we obtained this information using Roland's method. Thank you for that. and reconstructed it. And you can see also temperature development from four fire packages located in the combustion zone. So we can obtain information about temperatures in the fire, we can obtain heat fluxes, and also we can get information about wind vector. So you can see 3 wind components using our differential pressure sensors we use on fire packages. And these 2 dashed lines, they show start of the fire and end of the fire. And you can see that wind before the fire was, let's say, relatively stable, variations around plus minus 2 meters per second. Once we have flaming front arrived, we can see that wind profile changed, and we have much higher variations of wind components up to plus minus 5 meters per second. And what is interesting that after the fire, after the end of flaming combustion, we still have wind variations even in the smoldering combustion zone. Basically, when fire front passes, it's still a lot of smoldering combustion behind it, and that produces also updrafts and some turbulence there. Also, this example how rate of spread or mean rate of spread changes for different fire behaviors. You can see example of forward junction fires, linear fire fronts. So normal head fires, we call them linear fire fronts. Basically, it's normal fire, regular fire. Backward junction fires and parallel fire fronts. You can see that forward junction fires on average, they 3 times faster than normal fires or linear fire fronts. And after that, backwards fires and parallel fires, they relatively slow. But if we compare each particular fire which we studied, you can see that this is relative comparison of backward and forward junction fires relative to normal fire, parallel linear fire front, and you can see that some of the fires were 18 times faster than head fire. It tells you about the danger of junction fires. They can be very, very fast, depending on weather and fuel. Because we've done quite a lot of experiments in the last 5 years, you can see some of the results we combined together from different experimental campaigns. And this slide shows relationship between mean rate of spread and wind speed. And we can see that high wind speed, faster mean rate of spread on junction fires. And also these green lines from 22 experiment and this pinkish line from 23 experiment. And these are the different fuel types. This one was heathland, this one grassland. And you can see that for grasslands, mean rate of spread increases faster with increasing wind speed compared to heathland fuels. So fuel makes difference. This slide shows how mean rate of spread changes with junction angle, basically the angle between 2 fire lines. And as we expected, and it was shown in lab experiments as well, smaller junction angle, faster rate of spread, but after about 45 degrees, it doesn't make much difference. So it's kind of stable at the end. Another interesting result we found, this is the fire leg length, basically the length of one of the fire fronts, one of the V sides. And we can see that larger the fire, faster the rate of spread. And from 10 meters fire leg length to 50 meters fire leg length, rate spread increases more than twice in those experiments. So we did expect the scales somehow should impact on rate of spread, but we didn't expect it would be as high. Also, we participated in canyon fire experiment in 2022, thanks to colleagues from San Jose University. And it was a collaborative project. We were invited to use our fire packages to measure fire behavior characteristics. That was relatively big fire, 1 kilometer canyon, complex configurations. And you can see here fire packages we used together with Worcester Polytech Institute to measure heat fluxes, rate of spreads, and winds at the top of the canyon. This is the example how we positioned our fire packages. That's our fire package at the top of the canyon. WPI packages, they were permanent with equipment dug into the ground, but they had multiple heat flux sensors along the ground. We had only 3 in the same location. Temperatures and wind components as well. That's before the fire, and this is after the fire. So fire was quite intense. fuel was chaparral, and you can see almost everything gone, only a few sticks left. And this is the video of the beginning ignition line at the top of the canyon. Canyon goes up that way, and after the ignition, this is video. This video shows you kind of looking from the top of the canyon downhill, and you can see the flame heights. A very dark plume tells you about not complete combustion, which means that it's very intense and fast. And this scale gives you a sense of the size of the fire, 15 meters. You can see flames bigger than 15 meters. And these are electrical poles. So the fire was very intense once it reached the top of the canyon. And from our preliminary analysis, it tells us there was some eruption, basically acceleration, constant acceleration of fire front up to the hill. If you look at the data, what we found is the heat fluxes were ranging from 100 to 200 kilowatt per meter squared in that fire. These are isochronous reconstruction of fire front from the helicopter which San Jose University used with infrared camera, so they used another technique to reconstruct fire front propagation. And we also found residence time was around fuel combustion about 60-100 seconds. And some data from the heat fire packages in terms of heat flux and in different locations. So heat flux is for, let's say, the maximum fuel height or shrub height was about 1.5 meter, I think. And for that fuel, we had about 200 kilowatt per meter squared of heat flux, which is very significant, I would say. Also interesting results in terms of wind. This is U component of wind parallel to the ground. You can see again before the fire arrival, plus minus, I don't know, 2 meters per second. Once fire arrived, it was plus minus up to 10 meters per second updrafts. And similar to what we observed at small experiments in heathland in Australia, once fire arrived, wind changes significantly. And again, after the fire front passed, again, still variation in wind was up to 5 meters per second was observed, even after the fire. That was briefly about our field experiments. We also do a lot of research on spotting in wildfires and firebrands, and I've been working on this for quite a while. And I'm going to present some of the projects we've done and still doing. And if you're not familiar about spotting, spotting is a process of starting new fires at some distance from the main fire front through the firebrands transport. And firebrands are small particles which are generated in wildfires through burning of vegetation. Basically, vegetation breaks into small particles, and these particles are lifted by convective column or moved by the local wind along the ground, transported to some distance, and those firebrands, they land somewhere. And if they have enough potential to ignite, either smoldering or flaming, they can start new fire or they can ignite structures. And this is a huge problem in Australia because in Australia, vegetation, especially eucalyptus, it has a lot of bark, different types of bark, like candle bark, like big pieces of bark hanging from twigs, or stringy bark, very fibrous bark along the trunk. And those pieces of bark, they can travel in the convective column kilometers, even tens of kilometers. So for Australia, it's quite usual to have spot fires 5-7 kilometers from the main fire front. Sometimes we had cases where spot fires ignited 30 kilometers from the fire front. And a year ago was relatively small fire, maybe 10 hectares from the town where I live. And that fire was about, how many kilometers? 20 kilometers, I think. Huh? 60? 16.
This is the one in near Ballarat.
Yeah.
Oh,
60. Anyway, so I thought it's so far. I wouldn't expect any firebrands. I came home and I found firebrands as my finger in my backyard. That was unusual. Anyway, so this, as you can see here, spotting process consists of 3 main stages: generation, transport, and deposition. And we have very few knowledge about generation of firebrands. how much firebrands are generated, what are the sizes, what are the temperatures, shapes, and so on, because that would be important component for fire transport models, because they need to know how these firebrands be transported, how far, and if they would have ignition potential to ignite fuel or not. And we are working mostly on generation and deposition stages, trying to understand what is produced and if it has any ignition potential, because this is theoretically easy, can be done in the lab, and what we are doing. And the first project we are doing is conducted by my PhD student, Mohamed, and this collaborative work with University of Maryland in the US, Underwriters Laboratories Insurance Company, and also Fire Research Institute. And this project is focused on understanding ignition of building materials by firebrands, in particular firebrand pile accumulations, because in many cases when there is a complex topography, or in WUI fires, for example, the houses, they have complex shapes, they have entrainment corners, they have, I don't know, doors, frames, and so on, and firebrands can accumulate in different locations, creating piles. And these piles, they have much higher potential to ignite fuel than single firebrands. And what we're trying to understand is how these firebrand piles can ignite different structural materials. In our case, two types of decking materials, pressure-treated wood, which is pine, and Trex is a composite decking. I believe you can find anywhere in many countries. Basically, it's wood shavings combined with plastics, covered with a special film. And we tested deposition of firebrand piles, in our case 8 grams, roughly smaller than my handful, and different configuration of firebrand piles, parallel to the wind, perpendicular to the wind, with different properties of materials. And this is an example of our configuration. Firebrand pile is deposited on top of the decking material. Wind profile comes from this panel. And in some cases, in some experiments, we also used radiant heat flux additionally to the firebrand pile deposition. And we measured different characteristics for the combustion, mass loss, temperatures, heat fluxes, and use infrared cameras and so on. So you can see example of deposition of firebrand pile on pressure-treated wood, and engagement of the board, smoldering combustion, flaming combustion, and collapse of the board. And in some cases, fire propagated to the parallel boards, engaging other boards as well. And this example is for 2.7 meters per second wind speed, 7% moisture content of timber, and 90% 90-degree orientation of the firebrand pile. And during our experiments, we observed different phenomena. For example, pile ignition in flaming, flames coming from the pile itself, sample ignition when board is engaged and starts flaming, burn-through process, and back-surface flaming. So previously, all previous experiments are usually conducted in really small wind tunnels, where airflow and all characteristics can be very carefully characterized. But again, everything is about scale. We understand that once you get into real scale, where you have meters of fuel, when you have complex wind profiles, everything changes. And in our experiments, we tested 60 by 60 assemblies of decking materials, and we also compared the results to previous small-scale experiments in a small wind tunnel, only one board, which University of Maryland did. And that was the reason to understand how this scale affects on probability of ignition. And in our experiments, we found these two phenomena which haven't been observed before, like burn-through. For example, when firebrand pile accumulates on top of the materials, it burns through, engages board through the whole depth. And once it burned through, in some cases, we had back-surface flaming. Basically, once the flame becomes, the board ignites in flames underneath of the sample because of the complex airflow around the boards through the hole. And that results in complete combustion of the sample. So very dangerous situation. And some of the outcomes of the tests for pine samples, different levels of engagement, for composite material, none of them were ignited after firebrand pile consumed. That was what happened, extinguished, fully extinguished, no danger of combustion at all. So that was only firebrand pile exposure. And these are examples of the results. We've got, for example, probability of burn through. You can see different wind speeds we tested. configuration of firebrand pile and also moisture content of pressure treated wood. So these are results only for pine. And you can see that at high wind speed, probability of ignition almost 100%. Also 90% configuration of firebrand pile results in high probabilities of ignition, basically larger, longer side of firebrand pile exposed to wind, we have high probability of burn through. And also moisture content, low moisture content, high probability, which makes sense. Back-surface flaming, we observed only mostly at 2.7 meters per second. So it requires significant some level of wind to ignite it at the back in flames, some level of oxidation. For us, it was also interesting because we know that in real wildfires, firebrands, they're not coming alone. So sometimes, or in most cases, there will be some level of radiant heat exposure additionally. Like for example, firebrands can ignite some fuel around the houses, and those fuels, they produce flames, additional radiation. That radiation impacts on firebrands as well. And in Australia, there is a standard, we call it IS 3959, which is construction in bushfire-prone areas. So bushfire is wildfire. In Australia, we call it bushfire. Construction in bushfire-prone areas, basically any house which will be constructed somewhere where there is a risk of bushfires, it has to be assessed following the standard. And in that standard, bushfire attack level has to be assessed. So it tells you how much risk you have and how much exposure can be from fire if it initiates somewhere next to the house. And those bushfire exposures, they separated into 5 levels, 12.5 and so on to Bell of Z. So 12.5 means it is expected that will be 12.5 kilowatt per meter squared radiant heat plus additional impact of firebrands. And higher the risk, larger the radiant heat exposure, and the highest one, bushfire attack level flame zone, where high heat fluxes are expected, more than 40 kilowatt per meter squared, and also flame contact and firebrands. But if you remember from my previous slides, in chaparral fire, heat fluxes were 200 kilowatt per meter squared, much higher than our standard currently. And what we wanted to know is how additional heat flux would impact on our results, additionally to firebrand pile exposure. And initially we decided to let's test the lowest bushfire attack level, which is in standard, which is 12.5. And we applied 12 kilowatt per meter squared heat flux to our pine boards. And what we've got that in all cases, our boards were ignited and burned and collapsed. So this heat flux was too high to define the marginal conditions where we have ignition, no ignition. So when we decided to reduce it to 6 kilowatt per meter squared, which is relatively low, basically, that would be maybe twice higher than you have on very hot sunny day radiant heat flux. And these are results. Top one is, top one is 6 kilowatt for timber, and bottom one, top and kind of bottom view for the composite decking. And that was surprising for us that with very small additional amount of radiant heat, our composite decking engaged, and because it's mostly plastic, it melted, deformed, and collapsed at the end. And that tells us that even small amount of radiant heat addition to firebrand piles can ignite a lot of materials which are supposed to be non-combustible in some configurations. Another work we are doing with University of New South Wales in Canberra on understanding ignition probability of fuel beds, again by firebrand piles, but at high moisture contents, kind of simulating marginal conditions when there is ignition, no ignition. And we tested different vegetation types, pine needle litter beds, eucalyptus litter beds, different wind speeds, masses of firebrand piles, bulk density of fuels, again, without heat flux and with additional heat flux. And you can see some picturesque representation how we deposited firebrand piles on fuel beds. And this example of 2 experiments where we had relatively low moisture content, 5%, no wind, 1 gram of firebrand piles, and this one, 33% moisture content, 1 gram, 3 meters per second wind. So quite different conditions. One supposed to be no wind, very mild condition, but low moisture content, high moisture content, but with high wind. And this is the difference. And again, different acceleration of the video. So you can see after ignition, dry fuel ignited very quickly, burn out, very kind of circular fire shape, while at high moisture content, irregular fire front, but still burnt with wind and at high moisture content, but mostly on top of the fuel rather than the full layer combustion. And what you found, if you look at these results, you can see that this shows for pine needle fuel beds, this for eucalyptus fuel beds, different firebrand pile masses and probability of ignition. We can see that obviously higher firebrand pile mass, high probability of ignition, and also high wind speed, high probability of ignition. And if you compare two fuel beds, pine needle fuel beds has much higher probability compared to eucalyptus litter beds, which we could expect because eucalyptus litter beds, they have more coarser fuel, they have twigs, they have pieces of bark, and that impacts on ignition and propagation. And these results are for experiments with radiant heat flux and without additional one. And again, once we introduced radiant heat flux, we had almost twice higher probability of ignition for fuel beds. And again, for eucalyptus fuel beds, we had lower probability of ignition compared to pine needle beds. Okay, this our joint project with University of Corsica, where we're trying to understand multi-scale experimentation simulation of wildfire spotting, and this project consists of two parts. The first one is devoted to understanding amber generation or firebrands generation, and the second one on simulation of transport of firebrands. And the first part will be presented by Nin as the next presentation, and the second part will be tomorrow, which is led by Jean-Baptiste Filippi, with Alberto working on the project. And I'm going to quickly provide some overview of this project and also what will be presented by Nin after me. So the idea is, because we don't know much about firebrand generation, how many firebrands, because many people, I assume most of you are modelers, and some of you do transport of firebrands or any simulation with firebrands. I assume you don't have any data how many firebrands you need to inject in your model to transport them and to understand ignition probability. So all of these numbers, I assume, somehow made up. And what we're trying to do is to understand what types of vegetation produce how many firebrands they can produce, basically number of them, their size and shapes. So all of this information can be input as input data in the model of transport model, and that transport model will transport it and combust it and so on in the plume, and after that estimate where they land, the densities of landing, and also probability of ignition. And to do that, we need to know amount of firebrands generated. This is the first part of this project. So basically, we need to carefully predict fire rate of spread of fires. We need to know about spotting and firebrands, because at least in Australia it's a huge problem. So all fires, they propagate together with spotting. Spotting is a part of fire propagation mechanism. At short distance spotting, it's a part of basically fire front. If you firebrands ignite spot fires in tens, hundreds meters close to fire front, they merge and propagate. At long distance spotting, spot fires, they develop independently, and after that they can merge. And we need to know where and how they create and how they merge, and all of that would impact on rate of spread. So all of that information is essential. Respectively, we need to know where firebrands go into land, how many of them, and we need firebrand models. And to develop those models, we need to know how to describe our firebrands. We need to know information about firebrands, their sizes, shapes, volumes, temperatures, and so on. And to get this information, respectively, we need to somehow run experiments on firebrands to generate this information. And doing these experiments, we respectively need to know what we need to burn, what fuel we need to burn, how we need to burn it, in how much of that fuel we need to burn. And we need to understand what actual firebrand fuel is out there in the wildland, so we can carefully reconstruct it in the lab, burn it, and obtain all of this information. And this is a part of Nin's presentation, where he will be talking about this project. And this is it for me. Thank you very much.